Hello students, welcome to EPG Pathshala. I am Dr. Amarjit Singh from Himachal Pradesh University, Shimla. Today we are going to discuss about a module Crystalline Solids 1 from paper Solid State Physics. So the students, let's see what we are going to learn in this module. First of all, we will differentiate between amorphous solids and crystalline solids from the point of view of atomic arrangement, orders at different length scales. And next we will understand mathematical description of crystals in terms of unit cells. And then we will be able to differentiate between primitive cells and unit cells. What are these? And next objective is symmetry operations, translations, inversion and rotation. So what are crystalline solids? What do you understand? So if I tell in a very layman's language, I would say it's an aggregation of matter or atoms which are bonded together. Now when we say aggregate, now this can be aggregated in some pattern, some beautiful pattern, or they may not be arranged in a proper pattern. They may be just haphazard, just like that. So now we have to learn the language, how we are going to classify this crystalline solids, in how we are going to classify the material in terms of crystalline solids and amorphous material. So this solid state physics studies the structural, mathematical, thermodynamic, electrical, magnetic and optical properties. So this was just to outline and tell you why the crystalline solids are so interesting. What are the scope of these crystalline materials? Because the properties of the materials, as we discussed, either they are electric, magnetic and optical, they very much depend on how they are arranged at the atomic scale. Just for example, if you see the graphite and the diamond, so both are just pure carbon. Only that what is different in these two material is how they are arranged. So the atomic arrangement is such an important thing. It makes the properties of the material drastically different. The properties of the crystalline solids are determined by the symmetry of the crystalline lattice, because both the electronic and phononic systems which determine resistivity, the electrical, the magnetic and thermal response of solids are very sensitive to the regular atomic order of materials, and also how local perturbation in this lattice is also important. That also affects these properties. So in this slide we see that basic concepts of crystals we are going to talk about. So how you define a crystal, that is described in this slide. So you can see that it's written as basis plus lattice is equal to crystal, which is shown pictorially in the slide. So the lattice is a mathematical concept. One can draw any lattice by defining, let us say, two-dimensional lattice, any A and B axis, and putting these dots at some well-defined distances. That we can constitute a lattice like this. Now here basis is shown with a flower or a plant, just to illustrate, but actually in real solids these are complex molecules. The idea is that we are going to put each of these flowers or plants on this point, and we see that we form a crystal here. It is important to remember that we do not rotate this plant, it has a particular orientation. So we have to keep that orientation intact, and we see that these flowers are arranged in a very nice pattern. And from wherever any flower you go, this pattern is same. It remains constant. In any direction you look from the any plant, you see that it is all same. So this is an illustration of two-dimensional lattice. Similarly, one can construct a three-dimensional lattice by adding one more dimension, which would be perpendicular to the plane of this paper. Now, on the extreme right side, we see here an equation which writes Bravais lattice vectors in 2D. Rmn is equal to ma1 plus na2, where m and n are integers. So this is basically a mathematical representation of the same, which we have shown pictorially on the left. Here, if we follow this equation, the rule, first we define this axis a1 and a2. This dimension of axis is fixed, and now by using any integer m and n, 1, 2, 3, 4, 5, etc., you can go to any of the flowers in this. Basically, this equation is for the lattice. It represents the lattice, and one can, using this equation, one can reach anywhere on the flower in this crystal. So basically, this is a mathematical representation of this crystalline form which we have shown on this side. And if you want to show the same on the 3 dimension, then you add another dimension, PA3, something like this. Now this is further extension to the last concept which we discussed in the last slide. So here you see this is written as translation vector Tmn is equal to Rmn, has the following property. Here T represents, this is a translation vector, and Mn here is an integer. So basically it is shown that you can have several translations in a different way, and when you apply these translations, what is the law, mathematical law or algebraic law which they follow? This is represented on this slide. So additive law, first it says T PQ T UV is equal to T P plus U and Q plus V. This says that if you translate on a lattice by an integer U and V, and then you further translate with integer P and Q, now this will be is equal to as if you already add this subscript P and U, P plus U and Q plus U. So these on left hand side you have performed two separate translation, and this is one translation. So these translations are equivalent. So that is called additive law. And similarly you can see that associative law is there. It means if you are performing, let us say, first the translation operation Tmn, then Tuv, and on top of that you again apply some translation Tpq. So it is same as if you first apply Tmn, and on top of that you apply the product of Tpq and Tuv. So in any order you can perform these translations. It means that the result will be the same. And as you know the commutative law, it means that either you perform this TUV translation first and TPQ later, or you first perform TPQ and then TUV, result is same. That is what it means. And then this last is inverse law, which tells you that if you perform a lattice operation, a translation operation TPQ, and then you inverse the coordinates, I mean you make these coordinates negative, it will be equivalent to if you perform an operation t minus p minus q. I mean if you choose this integers p and q negative with respect to the earlier positive ones, the result will be the same. So this is mathematical extension of our concept described in last slide. A lattice, how small we can draw a lattice. Now when you ask this question from the point of view of mathematics, you can choose any small distance you like and also any large distance you like. But in real physical system, there are constraints like atoms and molecules, they have a size. So you cannot bring them closer to a certain particular distance. For example, if you put two hard spheres close, so there is a minimum distance of approach which is twice the radius. You cannot push them any further. Therefore, now this lattice vectors question is how small they can be. So a1 and a2, this is shown here in 2 dimension. So you can see that on the left it is written that modulus of the vector a1 and a2 are the lattice constants along the respective axis. So on the right hand side we have this a big square and there are some small rectangles, and then on the left hand side there is a shaded one. So here this a1 and a2, these are two primitive vectors which you have defined, and our lattice cannot be smaller than that. The idea is the area of this lattice is the smallest possible area of a given cell, or you also call this a primitive cell. Now you could define your lattice vectors, primitive lattice vectors, in other way also. Just like you see that below that there is a oblique shaded area. So this oblique shaded area shows you that there is a a1 and then a2 is oblique. Now the condition is this, that the volume or the area of this primitive cell and the primitive cell on the top has to be same, and only the direction of the vector is changing here. So below that we have shown two other cells. On the bottom corner this is a shaded cell which has a larger area, so that is not a primitive cell. And similarly another oblique on the right side, this also shows that this is not the smallest area possible. We can have a smallest area possible which are upper to 1. And on the this top right corner you can see that there is some irregular pattern drawn. So it shows that if the area of this irregular pattern is the same as that of primitive cell, then this can also be a primitive cell, but area has to be same. So that is the condition for this. Now it is written here, there are the area of the unit cell in 2 dimension, S is defined as a1 multiplied by a2. So in all these primitive cells the area is same. Now we are going to talk about what a primitive cell is. First of all, what a cell is in an crystalline solid. A unit cell is a just like a building brick, just as we use a brick to build a house, to build a wall. So is the smallest unit which you repeat one after the another, and by stacking these units you can make a big structure, a large structure. So similarly, using this unit cell you can make a large crystal. But the question here is, now this unit cell you can choose either to be small or larger or larger. So it depends on your choice, length scale of unit cell. But then there is a minimum limit to which you can choose this unit cell, and that unit cell of minimum volume is called primitive unit cell. You cannot choose unit cell smaller than that. So basically primitive unit cell is a kind of a special type of unit cell which is smallest in the volume. An equivalent definition of primitive unit cell is the cell with one lattice point. For example, if you take a simple cubic lattice, so in a simple cubic lattice you can see that there are 8 corners, and at each corner there is a one atom, or you can say a spherical atom. So this is just a model, the sphere is model. So 1/8 part of this sphere is inside the cell. Similarly, if you count 8 corner and 1/8 part, so this gives you just one unit cell, one atom in a unit cell. So this is a primitive cell basically. Non-primitive unit cells are larger than primitive unit cells, as we discussed last time. I just told that it can be a bigger cell, but are sometimes useful since they can exhibit more clearly the symmetry of the Bravais lattice. The point is that we may not always choose primitive lattice as to be our way of describing the crystals. We can choose some lattice bigger than the primitive lattice. Generally, it is very easy to describe the crystal in terms of symmetry if we choose the larger unit cell. Now, I will tell you something about symmetry operations. Symmetry operations are something in a crystal or in a given material that if you apply those operations and you leave the material invariant, or if you leave the crystal invariant, then these are called symmetry operations. Now the symmetry operations can be translation, it can be rotation of an object, it can be inversion, it can be mirror reflection. With these kind of operations, you could leave a given crystalline structure just invariant. It means it changes nothing. If you translate a from one lattice point to another lattice point by a given translation vector, it changes nothing from point of view of a structure or symmetry around that point. Similarly, with the idea of rotations and reflections, like that. And let us see, for example, we talk about a rotational symmetry and we have some geometrical figures, and now we call C1 as an operation. If we call C1 something as an operation, which operation means you rotate it by 2 pi or 360 degree, and let us see what is going to happen. So if you take, let us say for example, very irregular shape which has, it's difficult to define, and you rotate it by 360 degree with respect to some point, then you will see that you get back the same structure. So any kind of irregular structure is always symmetric about 360 degree rotations. Now there are some structures which are like you don't need to rotate them up to 360 degree. Even with the less angle than 360, you get the same structure. For example, a square. If you take the square, so if you rotate by 90 degree, you get the square again, same, no change in the structure. Like that, if you have a circle, you rotate it with any arbitrary angle and nothing changes with respect to the axis perpendicular to the plane of the circle. So that means the circle has highest degree of symmetry. Symmetry operations. So in this slide, we are going to demonstrate or show a rotational symmetry. Now you can see that rotational symmetry is expressed as a whole number n between 1 and infinity, and refers to the number of times a motif is repeated during a complete 360 rotation. So this will be clear below. You can see that there are different geometrical patterns, 1, 2, 3, 4 and 6 and infinity. So first let's go for this one, and now this has a particular geometry and there is a point in center. So if you rotate this geometry by 360 degree, then you get the same pattern. it means this n here is basically 1. So you have to give a one complete 360-degree rotation to get the same figure or the same pattern. Now let's come for this next one 2, and you can see there is a rectangle, and in midway here there is a point. So in this configuration, if you rotate it by 360-degree, twice it will happen that our structure or the orientation will match. First, when you rotate it by 180-degree, you get the same thing. Again you rotate it by 180-degree, and then you get the same thing. So basically it is written 2 here. Here n means 2. So when you rotate it by 360, it is the twice that you get the same orientation. Similarly, here we go for this equilateral triangle, and when you make a complete rotation of 360-degree, it is 3 times that you get the same structure or orientation of this triangle. I mean, after every 120-degree, you get the same orientation of this triangle. And now for the 4, it is not difficult to understand that it is a square, that when you rotate it by 90-degree, you get the square in the same orientation. So in 360-degree, it is 4 times that this orientation is repeated. So n is equal to 4 here, and in hexagon it is 6 times. You can see that one needs to rotate it by 60-degree to get the same orientation. So 6 times you get the same orientation in 360-degree rotation. And when you come to circle, you can see that it is infinity, because you can rotate it by any arbitrary angle and you get the same result. So basically it is by rotating, giving it a full rotation of 360-degree, it is infinite times that you get the same structure, or you can say it's highly symmetric structure. So when you talk about the symmetry, so the larger is the number of n, the higher is the symmetry of the structure. So in this slide we have illustrated how we talk about a rotational symmetry, and this number n here, which is represented as 1, 2, 3, 4, 6 and infinity, this number represents how symmetric the structure is. The larger the number, the higher the symmetry of this structure. Just like circle is the highest symmetric structure in this configuration. So in the symmetry operations, in this slide we illustrate a translation operation. Now you can see that we have shown here different stars, and there is a tx and tz axis. So it means that if you are in the center of this star and you go by this distance, this Bravais vector, then you repeat this way this structure. Again you move by Bravais vector, and then that is the center of the star, and again you move by a distance of Bravais vector, then this is the center of a star. This way one can construct, you can say, a crystal, or this represents an operation of translation, that you can go from one lattice point to another lattice point. So this is further continuation to the symmetry operations. Now this is inversion I, which is defined by the operation r goes to minus r if applied around the origin. So it is like we choose our origin, and we define the coordinate of a point which is represented by a vector r, and just giving a negative sign to it. I mean, inversion means we go onto the other side of origin. It means we apply this negative sign to all the x's present, or all the integers. Just you can see as in the figure above a and b, that you provide a rotation with respect to the center one, and this structure once again remains the same. So this is, one can say that there is an inversion symmetry. If you inverse this, r goes to minus r, nothing changes, it remains the same. That is what symmetry means. Now there is also a reflection symmetry, that's called sigma j, which can be applied around the horizontal plane, the vertical plane, or the diagonal plane. So this is illustrated here in this figure below, C, D and E. Now you can see that in D it is in the vertical plane, just as you have put an vertical mirror in front of one atom, and another atom will be reflected at the same distance. So this is reflection symmetry. And in E you see that the mirror is horizontally placed, and you can see this symmetry in the structure. C is this plane is not shown, but this is a diagonal. You can see that if you put a mirror across along diagonal, then you can see the reflection of one atom on the other side on the same distance. So this illustrates our inversion and reflection symmetry. So here in this slide we have shown or illustrated this mirror symmetry and inversion symmetry and reflection symmetry in slightly a better way. I mean, it's better to understand. You can see there is a rabbit on the left hand side. You place a mirror in front of rabbit and you can see the reflection of rabbit. So that is how a reflection symmetry is there. And so this is always a inversion. There is a plane involved here, and this is a reflection across this plane. In inversion symmetry, everything after inversion, everything is an equal and opposite distance through a single point. So in the reflection symmetry, there was a plane. Here it is a point, as you can see in the center at the eye, with respect to which everything is inverted. So you can see the rabbit has gone upside down. So that is just to illustrate a difference between reflection symmetry and inversion symmetry. So students, let us summarize what we have learned in this module. So first of all, we learned to characterize or differentiate the material in terms of crystalline solids and amorphous solids. Amorphous solids are basically solids which have no periodic arrangement or a kind of order in the crystal. There can be a short range order, like if you go from one atom to the next nearest neighbor, you could find some order to that length scale. But if you go on large length scale, you don't find any consistent order. Whereas in crystalline materials, that order extend to a very large distance, and in fact to a very macroscopic distance. So that is the main difference between this crystalline and amorphous materials. In the next, what we learned is that how to devise a mathematical scheme for working on the crystals. Like if you want to understand their symmetric properties and symmetry operations, you need to have a proper mathematical formalism, which you defined in terms of Bravais vectors, and we gave different symmetry operations, their different names. We learned about translational symmetry, inversional symmetry, rotation symmetry, and also we have understood the difference between unit cells and the primitive cell. So primitive cell is once again nothing but the special type of cell which is the smallest unit cell possible in the crystal. So that ends the learning about this module.